So the second speaker is the Professor In-sung Choe from Konkuk University in Korea. The title is The Symplectic and Orthogonal Heck Curves. Please.
Okay, thank you. I would like to thank the organizers for this nice opportunity to give a talk in this online seminar. And maybe, okay. Okay, this is This is based on joint work with Ki-ryong Chung, Jung Ki-ryong, and Lee Sang-hyun. And this is the first page is for the notation and the my plan of talk. And so throughout this talk, I assume C is a smooth algebraic curve of genus G, which is bigger than or equal to 2, to construct the moduli space of vector bundles. And like as you already saw this moduli space, as you see RL. Yeah, this is the moduli space of semi-stable vector bundles over C of rank R with the fixed determinant L of degree D. So when we don't want to, explicitly specify the line bundle L, we just write this way, SUCRD. And in my talk, I will discuss the generalization of the Heck curves on the moduli space to the moduli of symplectic bundles and orthogonal bundles. So these are the notations for these moduli spaces, MS and MO. And these are the plan of my talk. So first I review how to construct the Heck curves on the moduli space of vector bundles. Then I briefly...
Excuse me, is it possible to enlarge your screen to make it full screen?
Full screen? Okay.
He wanted to say Yunkai, but he wanted to maybe writing something on the right side.
Okay, okay, yeah. Okay, sorry for
that.
that.
Is there some problem to see?
Is it too small?
Well, no, not really a problem. Just just prefer to see something larger. So
okay, I see.
Okay.
Yeah, okay.
Maybe I'll make it. Sorry. Okay. Maybe I'll make it larger, and then. Oops. I'm sorry. Okay. Okay. Is it okay? Yeah. Yeah. So first, this is a plan of my talk. And first, I review the Heck curves on the moduli space vector bundles, and then briefly discuss the minimality of the Heck curves. And then I'll give a brief introduction to symplectic bundles and orthogonal bundles. And the third part is the main part of this talk, and this is construction of symplectic and orthogonal Heck curves. And then we have a similar result on the minimality of the Heck curves. And finally, I'll discuss the application of the Heck curves. There are two applications. One is non-abelian Torelli theorem, and another is the description of the automorphism groups of the moduli spaces. And here are most important references. The first one is a very old and fundamental paper by Narasimhan Ramanan on Heck correspondence and Heck cycles. The second one is by Professor Junmuk Hwang, and actually this paper is precisely AGEA in 2001. And then the third one, in this second reference, the Hecke curves are defined, and it's possible application to the geometry of the moduli space is discussed. And then the third paper, Choe proved the minimality of the Hecke curves on the moduli of vector bundles. And the last one is, I will explain the results in this last paper. And this will, I expect this appear in, this will appear in JLMS and maybe in this year. And if you want to find its preprint, is in this archive. Okay, so let me review the Hecke curves on the moduli space of vector bundles. So M is the moduli of vector bundles over C of rank R and determinant L. So for a general point of the moduli space, choose a mu, a linear functional of the fiber at X. Then we have a Hecke transformation in this star Hecke transformation. And if you restrict this Hecke transformation to the fiber at X, it will give you this 4-term sequence. And the corner is one-dimensional, of course. And then if you take a dual of the first Hecke transformation, we get an inverse Hecke transformation, and the V mu goes here and V goes here. And so this is a dual. And we can make it a family. We can make it family. So we choose a line L inside this vector space, which passes through L0. Then for each L in this line, we get this 3-star Hecke transformation. And in particular, when L is L0, it gives us the V dual, the 2-star sequence. So this shows us this the family of Hecke transformations. And if we take its dual, this gives a rational curve passing through the original bundle V. And this is called the Hecke curve in M. So is there any question on this construction? So there are 2 remarks. The first one is, so we need to confirm that each V tilde L here is stable, because we want a genuine rational curve inside the moduli of semi-stable bundles. So we need to confirm this one. And then also we want curve, not a point. So we want this one. So this is okay for under this genus assumption. And if we also assume this point is general inside the moduli space. So so from the construction, the Hecke curves are rational curves which cover the moduli space of vector bundles. So this is a covering family of rational curves. And from the construction, you can see that the parameter space of Hecke curves is actually Pn-2 bundle over Pn-1 bundle over C. So there is a double fibration over C. Because to construct the Hecke curve, we first chose a point X in C and a covector mu inside the Pn-1. And then we choose a line such that which passes through the point L0. And this line, these lines are parameterized by this vector space, which is Pn-2. So, so from the construction, the parameter space of Hecke curves passing through V are parameterized by this space, and more precisely, this is the projectivization of the relative cotangent bundle of this map. Okay, this is the brief review of the Hecke curves. And yeah, the moduli of vector bundles, this fixed determinant, this one has Picard number 1, and it is known that the anticanonical bundle is 2 times this is GCD of R and D times the delta, and where the delta is the ample generator of the Picard group. So I mean the modular space is a Fano variety of Picard number 1. And it can be computed that the Hecke curve have degree 2R. Here, degree means that the anti-canonical degree. And if you compute the degree in terms of the ample generator, you will see that the degree is 1 when d equals 0. So when d equals 0, we assume, R, by convention, R, the GCD is R. And the degree in terms of the ample generator is 1. So sometimes it's called the line. So in particular, in this case, you can see that the Hecke curves have a minimal degree. And actually, it is more generally, Choe proved that when G is bigger than or equal to 4, any rational curve passing through a general point of the moduli space has degree bigger than or equal to 2R. So this 2R is the minimal degree among the rational curves passing through a general point. And furthermore, it has degree 2R if and only if it is a Hecke curve. So in other words, if you think any covering family of rational curves of degree 2R, that family must be the family of Hecke curves. And the proof is obtained by examining the relative Harder-Narasimhan filtration of the family of bundles over this C cross P1. Yeah. So these results will be generalized to symplectic and orthogonal bundles later. So here I assume 2 applications. The first one is non-abelian Torres theorem. And if we have 2 smooth curves of genus G, and if the moduli spaces are isomorphic as projective varieties, then the base curves must be isomorphic. So because in this case the moduli spaces have Picard number 1, there is no issue of polarization, and we can just simply state in this way. So proof is very simple. Once we know the minimality of the Hecke curves. So if you assume these 2 moduli spaces are isomorphic, then the rational curves of minimal degree passing through V and the phi V, they are in 1-to-1 correspondence, because we know that we know that they are the parameter spaces are the double projective bundles over C and C prime respectively, because we know that that component should be the component of Hecke curves. And because the parameter spaces are rational fibrations over the base curve C, So we have the induced isomorphism of the curves. So this is the proof. And also with the similar idea, we can describe all the automorphisms of the moduli space. So there are two sources of automorphisms of the moduli space. One is the automorphisms coming from the automorphism of the curve. So if you have any automorphism of the curve, then you can pull back and to get the automorphism of the moduli space. And another source is an R torsion of the R torsion point of the Picard group. This tensoring by this tau, this gives an automorphism of the moduli space. And actually, one can show that every automorphism of the moduli spaces is just a composition of these two kinds of automorphisms. And the idea of proof is quite similar as the case of Nana-Belli and Torelli's theorem. So these are very nice application of the minimality of the Hecke curves. Okay, is there any questions so far? So I'll go to explain. I'm going to explain the symplectic and orthogonal bundles briefly. So I have to define so-called L-valued symplectic bundles or L-valued orthogonal bundles. So I first fix a line bundle of degree L, little l. And L-valued symplectic bundle is a vector bundle V equipped with an L-valued non-degenerate antisymmetric form. And of course, if we discuss the orthogonal bundle, the form must be symmetric form. So this is a family of symmetric vector spaces in some sense. I mean, symmetric or antisymmetric vector spaces. And the form can be also described as this isomorphism. So in the symplectic case, it must be antisymmetric isomorphism, and it must be symmetric in the orthogonal case. And from this isomorphism, we have this isomorphism. Yeah. Determinant V square is isomorphic to L to the M when M is the rank of V. And from this, we get this condition. Degree of V must be ML over 2. And in particular, when we consider the symplectic case, the rank must be even. So M equals 2n. And actually, we can show that the determinant must be isomorphic to L to the n. This is only for symplectic case. And so these are examples of symplectic and orthogonal bundles of low rank. So in the rank 2 case, so every rank 2 vector bundle is a determinant V valued symplectic bundle because every rank 2 vector bundle has this isomorphism. This is determinant V. And orthogonal bundles of rank 2, 3, 4. Yeah. So the direct sum of 2 line bundles, and this gives us an orthogonal bundle rank 2. In this case, these 2 line bundles are isotropic. And then so for rank 3 case, if you choose a rank 2 bundle E, rank 2, and then you take a second symmetric product, and that gives us orthogonal bundle of rank 3. And also, if we choose two rank 2 bundles, E1 and E2, and then take a tensor product, then that gives us orthogonal bundle of rank 4. And actually, all the orthogonal bundles of rank 2, 3, or 4 are can be constructed from these basic examples in some sense. So in some sense, these are all the orthogonal bundles. I mean, we need to make a statement more precise, but basically these are the most important examples of rank 2, 3, 4. And actually, in my talk, I'll discuss also orthogonal bundles of rank bigger than or equal to 5. So yeah, anyway, these are examples. So we need to discuss the moduli space of symplectic bundles and orthogonal bundles. So as before, we assume G is bigger than or equal to 2, and MS by MS, I denoted the moduli space of L-valued symplectic bundles of rank 2n, and because in the symplectic case, the rank must be even. And for the orthogonal bundles, I denoted by MOC, ML. And of course, to construct these moduli spaces, we need the notion of stability. And a subbundle is called isotropic if we stick to the symplectic or orthogonal form on that bundle that gives us 0. I mean, totally degenerate, then that subbundle is isotropic. And the symplectic or orthogonal bundle is called stable if we have this inequality for the slope for every isotropic subbundle. And yeah, these the dimension of the moduli space are known this way. And there are forgetful morphisms from the moduli of symplectic bundles to the moduli of vector bundles, and also from the moduli of orthogonal bundles to the moduli of vector bundles. These forgetful morphisms are generically injective because I mean this is just forgetting the symplectic form or orthogonal form, and there is a unique symplectic form or orthogonal form because we can assume the bundles are simple for a general point. There is a unique isomorphism up to constant multiplication. So these forgetful morphisms are generically injective. So in some sense, we can just assume that these two moduli spaces are embedded inside the moduli vector bundles. Okay, here are the overview of our results with Ki-Ryong Chung and Sang-Hyun Lee. So we first construct the Hecke curves. I mean the general version of Hecke curves on the moduli of symplectic and orthogonal bundles. And as a result, symplectic Hecke curves are just a special type of Hecke curves, ordinary Hecke curves. On the other hand, orthogonal Hecke curves are not the ordinary Hecke curves. Actually, it turns out that the degree of the orthogonal Hecke curve is twice the degree of the ordinary Hecke curve, as you will see later. And yeah, also we have the minimality result. So let script M be either the moduli of symplectic bundles or an irreducible component of the moduli of orthogonal bundles. Then the Hecke curves on M has the minimal degree among the rational curves passing through a general point. And conversely, I mean, if any rational curve of that degree, if you find any rational curve passing through a general point of that degree, then that rational curve must be the Hecke curve. I mean, here Hecke curve means symplectic and orthogonal Hecke curves. And we have a similar applications to the non-abelian Torelli theorem. And also we can describe the automorphism groups. So I will focus on the construction and then briefly discuss the minimality and the applications. So let me begin with the construction of Hecke curves. So as you see, this construction is precisely the same as the construction for the Hecke curves on the vector bundles. So actually, this page is identical with the previous page on the construction of Hecke curves. So we first, we start from a general point V, and then we take an Hecke transformation, and we get vector bundle V theta. Then we take a dual. This is a dual Hecke transformation. This was in the previous page. This was the 1 star, and this is a 2 star. And the sequence 2 star restricts to the fiber at X as the 4-term sequence. Then the next one is a 3 star sequence. This is a family version of the 2 star sequence. So if we take any linear functional of this vector space, then we can define a Hecke transformation to get V tilde lambda. And in particular, when lambda is chosen in this way, then we get back the V dual. So actually, this is the 2 star sequence. So this is a family. The 3 star is the family version of the 2 star sequence. So in the Hecke curve case, if we choose a line, we get the Hecke curve. But in our context, we need to keep track of the symplectic form. So compare this with maybe. So can I make it smaller? Yeah. So from the first star sequence, so V theta is a subshift of V, and also we can say that V minus X. So V minus X is a subshift of V theta. And from the dual sequence, we can say that V theta dual minus X is a subshift of V dual. Okay, so we have this subshift map, and this alpha is just this is alpha. This is alpha here. Okay, so we have this subshift map, and then omega is the antisymmetric isomorphism. This is isomorphism, and then alpha dual is just the dual of the alpha map. So composing these three maps, we get the skew symmetric map from V theta dual to the V theta tensor L dual 2x. Yeah. So we have some skew symmetric map which has some degeneracy. And in particular, if we restrict it to the fiber at X, it is always 0, because the induced map vectors through this vector space, which is the wedge product of one-dimensional vector space, and it is always 0. So actually we have this map. The image lands on the V theta tensor L dual X, not 2X. So we call this skew symmetric map by omega theta. So still this may have some degeneracy. And the degeneracy is computed by the kernel of the skew symmetric map. And it can be easily seen that the kernel has dimension 2, codimension 2. And so this skew symmetric map has degeneracy. And then as before, we constructed the family version of the Hecker transformation. And from that Hecker transformation, we have a similar sequence. And we can show that this induces an antisymmetric isomorphism if and only if the kernel is contained in this kernel. So as in the vector bundle case, we can always construct the first star, 1 star, 2 star, 3 star sequences, but the final sequence gives us a non-degenerate antisymmetric form if and only if we choose lambda which satisfies this condition. Yeah, this is I don't prove it, and it can be proven by a linear algebra. And so to get the symplectic bundle, we need to choose lambda in this vector space so that kernel of lambda is in the middle of these two vector spaces. And because this subspace has codimension 2, if we take a quotient is C2, so actually we have a P1 family of such choices. So once we start from once we fix theta, and then in the 3-star construction, we have just P1 family of symplectic bundles. Okay. So this is the symplectic Hecker curve. So we take the 3-star sequence under the condition that kernel of lambda contains the kernel of omega x theta. So this is isomorphic to P1, and this is called the symplectic Hecker curve. And actually, for technical reason, we have to prove the following proposition. So we assume G is bigger than or equal to 3, and 2n is bigger than or equal to 4, and we assume V is the general point of the moduli space. Then we can show that all the symplectic bundles from our construction are stable, and also the morphism from P1 to this C theta V given by this map is generically injective. So this gives us a genuine rational curve on the moduli space of symplectic bundles. Also, we know that this curve passes through V. So this is a symplectic Hecker curve. And from the construction, what is the parameter space? So to construct the symplectic Hecker curve, we choose theta in this vector space. And then in the dual process, we have only P1 family of choices to get a symplectic bundle. So there's no choice from the dual process. So therefore, the symplectic Hecke curves passing through V are parameterized by this projectivized bundle. So this is actually simpler than the parameter space of ordinary Hecke curves. And moreover, actually, if we assume these stronger conditions on the rank and genus, actually we can show that the PV dual effectively parameterizes the symplectic Hecke curves passing through V. I mean, any 2 points in this PV dual, if we choose 2 different points, then they correspond to different rational curves. So I think, yeah, maybe we can. This condition is not optimal, but anyway, we need some condition on rank and degree, rank and genus, to show this effective parameterization. So anyway, under some rank and genus assumption, you can show this. And also by construction, we see that the symplectic Hecke curves are precisely those Hecke curves on the moduli of vector bundles, which stay inside the moduli of symplectic bundles. As I said, this moduli space of symplectic bundles is embedded in this moduli of vector bundles. And those symplectic Hecke curves are precisely the ordinary Hecke curves lying inside the MS. So in particular, they have the same degree as the Hecke curve. And yeah, this is the story for symplectic bundles. And we can maybe do the similar thing for orthogonal bundles. So actually we expected this at the beginning, but actually it turns out that the same construction does not work for orthogonal bundles, because not every one-dimensional subspace is isotropic. For example, so in the symplectic case, we chose the wedge product of one-dimensional vector space, but in orthogonal case, we need to take a symmetric product, and this is not always isotropic. So we need some modification of the construction for orthogonal bundles. Anyway, is there any question so far? Okay, let me go to the case of orthogonal Hecke curves. So it's quite similar, but in this case, we have to choose a 2-dimensional subspace, not 1-dimensional subspace, and we need to choose isotropic 2-dimensional subspace. This IG2Vx is the isotropic Grassmannian. So we assume this V is an orthogonal bundle. So Vx is orthogonal vector space, and we choose an isotropic 2-dimensional subspace here. So because it's dimension 2, I chose the notation large theta. And then, as before, we take on Hecke transformation with respect to this 2-dimensional vector space, 2-dimensional subspace. And then we take a dual. This is 1 star, 2 star, and then 3 star. So here I chose the isotropic subspace because I want to minimize the degree of the rational curves. Yeah. So as you will see, yeah, this will make the degree smaller. And And the three-star construction is possible for any subspace of codimension 2. And if we choose any subspace of codimension 2, we get this three-star Hecke transformation. And then in particular, when lambda is this one, we get back the original bundle V. But as before, we need to keep track of the orthogonal form. So we begin with the in the second sequence, V dual is a subshift of V theta dual, but also we can say that V theta dual minus X is a subshift of V dual. So this is the alpha map. This is the alpha map here. And then we compose with the orthogonal form omega. And then we compose with the alpha dual. So this gives us a symmetric map from V theta dual to the V theta tensored by L dual 2x. So there is some degeneracy, but actually we can show that this restriction to the fiber at X is identically 0, because this map, actually this is the same as this symmetric map, and this map factors through this vector space. And because we chose theta to be isotropic, this is identically 0. So we can, actually the image of this map lands on L dual X, not 2x. So this is what I'm saying. Omega, we have a symmetric map omega theta, which lands on the V theta tensored by L dual X. And the kernel has codimension 4. And then, as before, we have from the three-star map, we have a similar kind of composition map, which is a symmetric map. And then we have a similar lemma as before. And this symmetric composition map induces a symmetric isomorphism from V tilde lambda to the V tilde lambda dual tensored by L dual, meaning that the V lambda is an orthogonal bundle, L dual valued orthogonal bundle, if and only if lambda is an isotropic subspace of So this subspace has codimension 4, and if we choose lambda between these two, then we get the symmetric isomorphism. So also this can be proven by linear algebra. And so this shows us that to get orthogonal bundle, we need to choose a two-dimensional isotropic subspace lambda bar inside this quotient space. I mean, this one by quotient by this one, and this is C4. This is C4. I mean, this is C4 with the orthogonal form. I mean, this is there is a non-degenerate symmetric form, and we need to choose a two-dimensional isotropic subspace inside this orthogonal vector space of dimension 4. So the parameter space should be this one, IG24, and it is well known that this IG24 is disjoint union of two copies of P1, like the two rulings of the quadratic surface. So IG24 is 2 copies of P1. Then among the 2 lines, we choose the line containing this point because we want to recover the original vector bundle. So we choose this P1, this P1, this one, and then we take a family of P1 family of vector bundles, P1 family of orthogonal bundles, and this is the orthogonal Hecke curve. And this here is a technical proposition. We assume G is bigger than 5, M is bigger than 5, and then we choose V as a general point of the moduli of orthogonal bundle. Then we can show that all the constructed orthogonal bundles are stable, and the morphism from P1 to this C theta V is generically injective. So this gives us a genuine rational curve. So under this assumption, we get a genuine rational curve inside the moduli space of orthogonal bundles, which passes through the point V. So this is called an orthogonal Hecke curve. Okay. And what is the parameter space? So to construct an orthogonal Hecke curve, we have chosen theta, large theta, here. And then in the dual process, there was P1 union P1 family of choices to get orthogonal bundles. But I mean, yeah, there are two rational curves. We can construct 2 rational curves, but the line containing the point, this point, gives a line passing through V. And another line is expected to lie inside the other component of I mean, this moduli space is not irreducible actually. This is 2 irreducible components, and the 2 components are classified by so-called Stiefel-Whitney class. And we expect that another line lie inside another component. So here is, I think, here can be another interesting story, but we didn't study this further. So anyway, this shows us that there is, as in the symplectic case, we have no choice from the dual process. So therefore, the orthogonal Hecke curves passing through V in the component containing V are parameterized by this variety. So the first choice of large theta will give us one Hecke curve, orthogonal Hecke curve. And actually, moreover, if we assume this condition or this one, then we can show that this IG2V effectively parameterizes the orthogonal Hecke curves through V. Also, these restrictions are not optimal, but certainly there should be some condition on the rank and genus to guarantee the effective parameterization. And from the construction also, we can see that orthogonal Hecke curves are not the Hecke curves on the moduli of vector bundles. In particular, they have the degree twice as large as the degree of Hecke curves, because we chose 2-dimensional subspace, not 1-dimensional subspace. And this page is for I mean, technical reason, and we need this. Actually, we need this technical result because I mean this lemma explains why we need this rank assumption and genus assumption. So if you choose any general point of the moduli of symplectic bundles or orthogonal bundles, and let phi be a non-zero map of vector bundles such that the difference of the degree is delta. Then actually we can show that that is the unique map from W to V under these assumptions. If we assume this or this. So if W and V have a very small degree difference, then there is a unique morphism, unique map from W to V up to constant. So this is a technical result to guarantee the effective parameterization and so on. Yeah. So the idea is from Narasimhan and Ramanan's paper, but we should so in the dimension counting, we should pass to the language of isotropic subbundles, and there is some technical way to do this, and we can show this lemma. And let me discuss briefly on the degree of Hecke curves. Under these assumptions, the Picard groups of the modular spaces are again infinitely cyclic. So there is no issue of polarization, and there is a generically injective forgetful morphisms to the modular vector bundles. So to compare the degree with the degree of ordinary Hecke curves, we choose this polarization. I mean, we choose the anti-canonical line bundle on the modular vector bundles, and then we pull back it to the modular of symplectic and orthogonal bundles, and then we compute the degree of rational curve in terms of this pullback line bundle. So the theorem is as follows. Let M be a component of the moduli spaces, and under this genus and rank assumption, the symplectic Hecke curve have degree 4m, and orthogonal Hecke curve have degree 4m. So actually these are different because we assume 2n here and m here. Okay, so actually the degree of orthogonal Hecke curves is twice the degree of symplectic Hecke curves. And finally, most importantly, we can show that the Hecke curves have minimal degree among the rational curves passing through a general point. And also conversely, we have a rational curve passing through a general point over this degree 4n or 4m. Then that rational curve must be symplectic or orthogonal Hecke curve. So this is what we can prove. The proof is we in some sense we borrow the proof of Schauter's son in the case of Hecke curves on vector bundles, but we need some modification, of course. And this is the modification is from the Harder-Narasimhan filtration of symplectic and orthogonal bundles. So I think this lemma is quite known to the experts, but we could not find any reference, and we proved it in a very elementary language, and the result is as follows. So let P1 be a rational curve inside the modular vector bundles, and then we further assume that they lie inside the subvariety of modular space of symplectic or orthogonal bundles. Then actually we can find the chain of isotropic subbundles such that then we can make it twice longer by flipping via the pulp construction, because in the symplectic and orthogonal case we have a pulp construction. So we have this we have this mirrored sequence. So here is the original sequence, and here is the mirrored sequence. And this bundle, and this bundle in the middle are symplectic or orthogonal. So this is a special feature of symplectic or orthogonal bundles. So the Hadamard filtration has this type of special type of filtration. So this shows us that we can actually compute the degree of the rational curve by using isotropic subbundles only, because these bundles are isotropic, and then by using this left-hand part, we can compute the corresponding part, right-hand part. So yeah. So because we can control the isotropic subbundles are controllable in the symplectic and orthogonal setting, we can manage to compute the degree of the rational curves. This is the modification we need to compute the degree of Hecke curves, and that gives us the previous results. Okay, and finally, we can have a similar application for moduli of symplectic and orthogonal bundles. So we assume these rank and genus condition to guarantee the effective parameterization of these parameter spaces. And under this assumption, we have this Nana-Bellian-Torelli type theorem. And the proof is just identical as before. Because also in this case, the parameter spaces are rational pi variations are over C and C prime. So the isomorphism of the parameter spaces induces the isomorphism of the base curves. And also we have an application, we can describe all the automorphisms of the moduli spaces. And actually in this case, as before, there are two sources. One is automorphism of the curve. Now another source is two torsion points. So in this case, not R torsion, but two torsion points, because we need this isomorphisms. And we can show that, yeah, actually the automorphisms are described, the automorphisms of the moduli of symplectic bundles are described earlier by other people. And I think the automorphisms in the orthogonal case are not described before. And this is our new result. This is under the previous assumptions on genus and rank. The automorphism groups of the moduli of symplectic and the orthogonal case. So in the orthogonal case, we should make it precise. Let M be the component of the orthogonal moduli of orthogonal bundles containing the trivial orthogonal bundle. Then we can show that the automorphism is generated by these two sources. The proof is quite similar as before. Okay, okay. This is the end of my talk, and this picture is taken from Ulsan last month. Thank you for attention.
Okay, so thank you very much for nice talk. Any questions or comments?
How about if you look at rank 7 bundle with G2 structure?
Rank 7?
Yeah, instead of 2 form, you look at 3 forms.
Ah, 3 form.
Yeah, so a generic free form determine a G2 structure. on a rank
Okay,
7 like a
okay.
bundle. Yeah.
I understood. So you mean how about the another G bundles?
Yeah.
Yeah. That that I haven't thought about that. Yeah. I don't know. Sorry.
I mean, the next
So,
simplest one is probably
Yeah,
G2, I
because
think. Yeah.
our technique, I mean, as you know, the symplectic and orthogonal bundles can be treated as a bundle with some extra structure. So
That's why
technically,
I asked. That's
yeah.
why I say
And,
G2, because it's just a free form,
yeah.
non-degenerate free form.
For exceptional groups, I think we certainly need some group theoretic approach, and this kind of approach does not. We need a different approach, I think.
No, but for G2, for example,
Yeah.
it's just from non-degenerate two form now it become non-degenerate free form. I mean, so it's completely controlled by this free form, similar to the symplectic case.
Okay.
Yeah.
Okay.
And it's in the linear algebra, it's pretty much
Okay.
very well understood too. Yeah.
Okay. Yeah. I haven't thought about that. Sorry.
Yeah.
Okay. Other questions or comments?
I have a question.
Okay.
So it might be slightly irrelevant question, but do we know any other kind of global geometry of the moduli of symplectic bundles and orthogonal bundles, like rationality, for instance?
Rationality. As I know, of course, as you see, as I already mentioned, the moduli of symplectic orthogonal bundles are related to the moduli of vector bundles, and there are some simple observations from that relation. I mean, because we have some results on the rationality on the moduli of vector bundles, and we can, in some sense, pull back in some special case in obvious way. So I don't know any other results other than the kind of yeah. So for example, yeah, rationality. I don't think nothing is known for example, for symplectic bundles. For example, the symplectic bundles of rank 2 is a vector bundle of rank 2, and in that case, yeah, we can just borrow the results from the vector bundle case. But for higher rank case, I don't think, yeah. Yeah, that's an interesting question, I think. Yeah.
So are there
But
cases that, yeah, sorry, go ahead.
Sorry, yeah, please.
I was saying, are there cases like the moduli space of bundle come with automorphism such that the fixed point set gives you this symplectic structure moduli space or orthogonal moduli space?
Pardon? What? Can you?
Questions.
Yeah.
Are there examples, maybe special cases, that the moduli space of bundle admit an automorphism where the fixed point set gives you this this type of moduli with symplectic or orthogonal structure?
So the moduli of symplectic orthogonal bundles can be described as a fixed point of certain.
This question, yeah, it's a question. Yeah.
I don't think so, because I already listed there is a complete list of finite set of finite group of automorphisms. The automorphism group is finite, and you can just yeah. So I don't think so.
So let's say, for example, when the curve admit some being a double cover of some other curve, things like that. I mean, that's why I'm thinking about special cases. Yeah. The curve itself is extra automorphism. Yeah.
Yeah, but the automorphism group is always finite, and
we only need one automorphism group. Automorphism.
And the dimension of the symplectic and orthogonal bundles are very small compared to the
Yeah.
modular vector bundles. So
Yeah.
I don't think so. Yeah. Yes, I think the modular symplectic orthogonal bundles are much smaller than the fixed locus, I think.
Why?
But that's I didn't check
I
it,
see.
but that's my my guess.
No, I was
Just my
thinking
guess, yeah.
maybe when the curve is very special, like being a double cover or something, and then this
Okay.
extra automorphism might
Okay.
induce a very special automorphism on the modular space of bundle,
Uh-huh.
and a fixed point set may be special. Yeah.
Okay.
Yeah.
Mhm.
Okay. Any other questions? By the way, all of them are Fano, this moduli.
Yeah. All of them are
All of
Fano.
them are
Yeah.
Fanos. But
Yeah.
but it might be not irreducible. Right? Some are.
Yeah. The orthogonal case is not irreducible. Yeah. There are two connected components. The symplectic case is irreducible.
Okay, other questions? Okay, if not, then let us thanks again to the speaker for
Okay.
nice talk.
Thank you very much.
Okay, so thank you very much for participating today's seminars, e-stage seminars. So maybe let's meet maybe some week later. Okay, thank you.
Yeah, thank you.
So have a nice lunch. Okay, thank you.